Far beyond the reach of sunlight, in the western Pacific Ocean, lies the deepest known place on Earth, the Mariana Trench. Stretching over 2,500 kilometers, this vast underwater chasm descends nearly 11 kilometers below sea level. It is a world of crushing pressure, absolute darkness, and mysteries humanity has barely begun to understand. Subscribe for more deep ocean mysteries grounded in real science and history. The trench formed millions of years ago where the Pacific Plate slides beneath the smaller Mariana Plate. This process, known as subduction, slowly bends the Earth's crust downward. Over geological time, the collision carved a scar so deep that even Mount Everest could fit inside it, completely submerged beneath the ocean. At the trench's deepest point lies the Challenger Deep, a depression reaching nearly 11,000 meters below the surface. The pressure here exceeds 1,000 times that at sea level. Every square inch endures forces so immense that ordinary materials would collapse instantly. Yet, despite these extremes, life persists. For centuries, the trench remained pure speculation. Early ocean maps marked the Pacific depths as featureless voids. It was not until 1875, during the HMS Challenger expedition, that weighted soundings revealed astonishing depth. Even then, scientists struggled to believe the measurements were accurate. Modern sonar mapping in the 20th century confirmed the trench's staggering dimensions. Pulses of sound sent downward returned far later than expected. Each refined survey revealed sharper contours, steep walls, and an abyssal plain descending into darkness. Yet sonar could only outline shape, not reveal what truly existed below. In 1960, Jacques Piccard and Walsh descended into Challenger Deep aboard the bathyscaphe Trieste. Their steel sphere creaked under unimaginable pressure. For 20 minutes, they witnessed drifting sediment and faint signs of life. Then they ascended, leaving the trench largely unexplored for decades. Nearly 50 years passed before another human returned to the bottom. In 2012, filmmaker James Cameron completed a solo descent in the deep-sea Challenger. Advanced cameras captured alien landscapes of pale sediment and strange organisms. Even with modern technology, the visit lasted only hours. Pressure at those depths reshapes biology. Creatures of the trench lack air-filled cavities. Their bodies rely on flexible membranes and specialized proteins that function under extreme compression. Fish discovered there appear translucent, fragile, yet perfectly adapted to a world that would instantly crush surface life. Among the trench's most remarkable inhabitants is the Mariana snailfish. Its gelatinous body and delicate fins seem impossibly soft, yet it thrives at depths beyond 8,000 meters. Scientists once doubted vertebrates could survive such pressure, but the snailfish proved evolution's adaptability extends further than imagined. Giant amphipods roam the trench floor, scavenging organic debris that drifts from above. Some grow far larger than their shallow water relatives, a phenomenon known as deep-sea gigantism. With few predators and slow metabolisms, trench creatures conserve energy in an environment where food is scarce. Bioluminescence flickers in the darkness above the abyss, creating brief sparks of cold blue light in a world without sunrise. Many trench organisms generate light through chemical reactions inside specialized cells, using it to attract prey, confuse predators, or communicate silently. In the Mariana depths, illumination is biological, fragile, and fleeting. Despite its remoteness, the Mariana Trench is not untouched by humanity. Microplastics and industrial pollutants have been detected in sediment samples collected from Challenger Deep, carried by ocean currents. Contaminants eventually settle even in the planet's most inaccessible places, proving that no depth is beyond the reach of surface activity. The trench plays a subtle role in Earth's long-term carbon cycle. Organic matter sinking from surface waters accumulates in deep sediments, where some becomes buried for geological timescales. Through subduction, portions of this carbon are drawn into the mantle, influencing atmospheric chemistry over millions of years. Powerful earthquakes frequently occur near the Mariana subduction zone, where tectonic plates grind relentlessly against one another. Some of the deepest seismic events ever recorded originate here, hundreds of kilometers below the surface. These quakes reveal immense forces operating silently beneath the trench's seemingly calm waters. Along the nearby Mariana volcanic arc, hydrothermal vents release mineral-rich fluids heated by magma below. Though not located directly within Challenger Deep, these systems demonstrate how life can flourish without sunlight. Entire ecosystems rely on geosynthesis, transforming chemical energy into biological productivity in extreme isolation. Scientists suspect that countless microbial species remain undiscovered within trench sediments. Each expedition retrieves new extremophiles capable of surviving intense pressure and near-freezing temperatures. These microorganisms possess unusual metabolic pathways, offering potential insights into biotechnology, medicine, and even theories about life beyond Earth. Sound behaves differently in the deep Pacific. Low-frequency acoustic waves travel efficiently through dense water layers, allowing researchers to map the seafloor remotely. Yet echoes from the trench often return distorted or faint, reflecting complex terrain and thick sediment that absorb and scatter acoustic signals unpredictably. At the bottom, sediment forms a soft layer known as abyssal ooze. Composed of microscopic shells, organic fragments, and fine mineral particles, it settles slowly over thousands of years. These layers act as geological archives, preserving subtle records of climate shifts, ocean chemistry, and biological evolution. Temperatures in Challenger Deep remain just above freezing, creating a stable yet hostile environment. Combined with crushing pressure, this cold slows chemical reactions and biological activity. Organisms that survive here operate at minimal energy levels, conserving resources in a realm where nutrients arrive only gradually from above. Although the trench appears isolated, deep currents flow along its contours, delivering oxygen and suspended particles. These slow-moving waters shape sediment distribution and influence where organisms can thrive. Even at nearly 11 kilometers below sea level, the Mariana Trench remains connected to the dynamic circulation of the global ocean. Some researchers speculate that undiscovered mineral concentrations lie hidden beneath Mariana sediments. Subduction zones can concentrate rare elements under intense heat and pressure. Yet extracting resources from nearly 11 kilometers below sea level remains technologically unrealistic. The environmental risks alone would outweigh potential economic benefits in such fragile ecosystems. Most modern trench exploration relies on robotic landers and remotely operated vehicles. These machines descend slowly, enduring immense compression while transmitting images and data to the surface. Many missions fail when electronics malfunction under pressure, reminding scientists how unforgiving the Hadal environment truly is to engineered systems. Occasionally, unexplained acoustic signals are recorded in deep Pacific waters near the trench. While most sounds originate from tectonic activity or marine organisms, certain low-frequency patterns remain difficult to classify. The trench's extreme depth alters how sound travels, sometimes amplifying, bending, or distorting vibrations in unexpected ways. Life in the trench depends heavily on marine snow, a continuous drift of microscopic organic debris descending from surface waters. These particles provide essential nutrients to scavengers and microorganisms. Without this slow, steady rain of matter, sustaining biological communities at such depths would be nearly impossible over time. When a whale carcass sinks into abyssal depths, it creates a temporary oasis known as a whale fall. In the nutrient-poor trench environment, such events support complex communities for years. Scavengers, bacteria, and specialized organisms consume the remains, transforming death at the surface into life below. High-pressure laboratories on land attempt to replicate trench conditions inside reinforced chambers. Scientists study how cells, enzymes, and proteins function under compression similar to Challenger Deep. These experiments reveal molecular adaptations that stabilize biological structures, expanding understanding of how life persists at extraordinary depths. The Pacific Plate continues sliding beneath the Mariana Plate at several centimeters per year. This steady motion gradually reshapes the trench, deepening certain sections while altering others. Over geological time, the landscape evolves slowly, driven by tectonic forces far more powerful than any human influence. Satellite measurements detect slight variations in gravity above the trench, caused by differences in crust thickness and mantle density. Though subtle, these anomalies help geophysicists map structures hidden beneath kilometers of water. Even from orbit, the Mariana Trench leaves a measurable imprint on Earth's gravitational field. The Mariana Islands rise above the ocean as visible evidence of the subduction process shaping the trench below. Magma generated deep within the Earth feeds volcanic activity along the arc. What appears as tropical islands at the surface is directly connected to the immense forces carving the abyss beneath. Some scientists theorize that microbial life may extend deep into the oceanic crust beneath the trench floor. These extremophiles could survive entirely on chemical reactions driven by tectonic heat. If confirmed, such ecosystems would expand known limits of life, suggesting that biology thrives wherever energy exists. Deep-sea exploration remains among the most expensive scientific endeavors on Earth. Specialized vessels, pressure-resistant submersibles, and advanced robotics require enormous investment. Each descent into the Mariana Trench demands careful engineering and calculated risk. Despite the cost, researchers persist, driven by the understanding that profound discoveries often lie in extreme environments. Remarkably, more humans have walked on the moon than have descended to Challenger Deep. This comparison highlights how inaccessible the trench remains. Space travel, though complex, avoids crushing pressure. The Hadal zone presents a different challenge entirely, one defined by relentless compression and technological fragility. High-resolution sonar mapping has revealed that the trench is not a simple crack in the seafloor. Instead, it contains terraces, ridges, and steep escarpments shaped by tectonic strain. These features create a varied landscape resembling underwater mountain ranges descending into an immense central depression. Water density increases slightly under extreme pressure, altering buoyancy calculations for deep-diving vehicles. Engineers must account for subtle changes in compressibility when designing descent systems. Even small miscalculations can compromise structural integrity in an environment where external forces exceed 1,000 atmospheres. Communication with submersibles at such depths relies primarily on acoustic signals. Radio waves cannot penetrate dense seawater effectively. Messages travel slowly as sound pulses, limiting bandwidth and increasing delay. In the trench, communication is minimal, deliberate, and carefully structured to prevent signal confusion. Autonomous underwater vehicles now patrol portions of the trench for extended periods, collecting continuous environmental data. Equipped with sensors and cameras, they record temperature, salinity, and pressure variations. These long-term observations reveal patterns that short expeditions might overlook, gradually improving scientific understanding. Certain trench microorganisms metabolize hydrocarbons, sulfur compounds, and dissolved metals as energy sources. Their unusual chemistry challenges traditional biological models based on sunlight. By exploiting chemical gradients, these organisms demonstrate that life can adapt to environments entirely disconnected from photosynthesis. Powerful earthquakes occasionally trigger sediment avalanches along trench walls. These underwater landslides reshape the seafloor, burying organisms and altering habitats. Such sudden events contrast with the otherwise slow pace of Hadal processes, reminding scientists that dynamic forces remain active even in extreme depths. Though isolated, the trench interacts with global ocean circulation through deep currents and water mass exchange. Nutrients, oxygen, and heat flow gradually through the abyssal network. Challenger Deep is not a sealed void, but part of a planetary system linking surface climate with the deepest ocean basins. Marine biologists believe countless trench species remain undiscovered due to limited sampling coverage. Each expedition retrieves unfamiliar organisms, many fragile and poorly understood. Given the vast area and depth involved, the Mariana Trench likely hosts biodiversity far exceeding what current records suggest. High-resolution cameras lowered into the trench occasionally capture delicate tracks etched across the sediment. These faint trails suggest slow-moving creatures navigating the darkness, leaving temporary signatures in soft abyssal ooze. Often, the animals themselves remain unseen, reinforcing the sense that much of trench life moves just beyond observation. Major seismic events along subduction zones can generate tsunamis that travel across entire ocean basins. While the trench floor lies far below surface disturbance, the tectonic forces responsible for its depth are directly linked to these powerful waves. The deepest point on Earth influences coastlines thousands of kilometers away. Long-term monitoring stations anchored near the trench record subtle fluctuations in temperature, pressure, and current speed. Over years, these datasets reveal gradual environmental shifts invisible to short missions. The abyss changes slowly, but it does change, responding to tectonics, climate variation, and ocean circulation patterns. Even precise depth measurements of Challenger Deep vary slightly between expeditions. Differences in instruments, pressure calibration, and sea conditions create minor discrepancies. These variations remind scientists that absolute precision in extreme environments remains challenging, and that the trench still resists perfect quantification. Polymers extracted from trench organisms exhibit unusual flexibility and stability under compression. Materials scientists study these biological compounds to design pressure-resistant technologies. Adaptations forged in darkness may inspire innovations for medicine, engineering, and even future exploration vehicles built to endure hostile environments. For many researchers, the Mariana Trench represents more than geological curiosity. It embodies Earth's capacity for extremes, where crushing pressure and freezing temperatures coexist with fragile biological systems. Each descent reinforces humility, demonstrating how little of the planet's interior ocean humanity truly understands. Despite decades of study, vast sections of the trench remain unmapped in detail. Shadows persist between survey lines, and unexplored ridges descend into unknown depressions. Technology improves steadily, yet the abyss continues to reveal itself only in fragments. The Hadal zone challenges assumptions about habitability. Where light never reaches and pressure seems unbearable, life adapts with quiet persistence. The trench proves that boundaries once thought absolute are instead invitations for deeper investigation. Standing on a ship's deck above Challenger Deep, the ocean appears calm and ordinary. Beneath that surface lies nearly 11 kilometers of descending water, sediment, and darkness. The contrast between surface serenity and hidden abyss underscores how deceptive appearances can be. In the end, the Mariana Trench remains a frontier not because it is unreachable, but because it is barely understood. It holds records of Earth's past, clues to life's resilience, and forces still shaping the planet. In silence and darkness, the deepest place on Earth continues to endure.